For this circuit, we are to determine the impedance ZL for maximum average power transfer and the value of the maximum average power transferred to this load. We will first determine the Thevenin equivalent circuit for this network without the load attached. The open circuit voltage VOC can be determined from this network, which, by the way, is the Thevenin voltage VTH. This open circuit voltage can be calculated in a number of ways. For example, we can start by computing the current I. The solution is not at first obvious. So in order to calculate the current, I'm going to disregard VOC for the moment and rearrange the circuit like this. To calculate the current I, we will use Ohm's law. The current I flowing through the capacitor and resistor is given by the voltage drop across the series combination, which is 18 volts all over the series impedance combination, which is 1 minus J. Substituting these values in our equation yields 18 divided by the quantity 1 minus J amps. Since we now know the current I, let's go back to the original diagram and proceed with the rest of the calculations. Returning to our original circuit without the load, next we would like to calculate the voltage drop across the 1 ohm resistor, which I have labeled V subscript R. And we know that the only current flowing through VR is the current I, which we have just calculated. So VR equals IR, Ohm's law. Substituting the actual values, we get 18 divided by the quantity 1 minus J times 1, which equals 18 all over 1 minus J. We can now calculate VOC, which is the voltage drop VR minus the 6-volt power supply voltage. Substituting the actual values, we get 18 divided by the quantity 1 minus J minus 6. Now I want minus 6 to be in a different format, so I'm going to multiply it by 1, or 1 minus J divided by 1 minus J, which is 1. Rewriting the fractions, I get 18 minus 6 plus 6J all over the quantity 1 minus J, which reduces to 12 plus J6 all over 1 minus J, or in polar notation, it equals 9.49 at 71.56 degree volts. This is also our Thevenin voltage. The Thevenin equivalent impedance is obtained by looking into the open circuit terminals with all sources replaced. In this case, we replace the voltage source with short circuits. Note that the 1 ohm resistor on the left is shorted, hence we can simplify the circuit like this to make it easier to analyze. ZTH then is equal to the 1 ohm resistor in parallel with the 1 ohm capacitor, which gives us minus J all over the quantity 1 minus J ohms. Once again, I want the fraction in a different format, so I'm going to multiply by 1 plus J all over 1 plus J, which is the same as multiplying by 1. Working out the math, we are left with 1 minus J all over 1 plus 1, which leaves us with 1 minus J all over 2, or 1/2 minus J 1/2 ohms. Now we have the information required to represent the Thevenin equivalent circuit. Now let's put back the load, ZL, and analyze our circuit. For maximum average power transfer, ZL must equal the conjugate of the theta impedance, ZTH. Therefore, ZL is equal to 1/2 plus J 1/2. We can now replace the circuit elements with actual values in the circuit diagram and calculate for the current. According to Ohm's law, I is equal to the source voltage divided by all of the impedances in the circuit that are in the circuit. The denominator very conveniently works out to just 1, which means the current phasor is identical to the voltage phasor, 9.49 at an angle of 71.56 degrees. This means the current in the circuit is in phase with the voltage. This should not be surprising because we are shooting for maximum power transfer, which means reactive components of this series circuit will cancel each other out. Therefore, the current providing real power is just the magnitude of the current, which equals 9.49 amps. Remember that the power delivered to the load is given by I squared R, which in actual terms is 9.49 squared times the load resistance, which is 1/2 ohms, and that is equal to 45 watts. And we're done. In recent years, the reality of climate change has become impossible to ignore. Severe weather events are growing more frequent and more intense. For homeowners, this means that utility power outages are no longer inconveniences. They can last for hours, days, or in extreme cases, even longer. The question is no longer if, but when. You'll need a solution to keep your homes powered and your family safe. When it comes to residential power backup, EcoFlow offers a range of solutions suitable for everything from powering a single appliance during a short outage to running an entire home in the event of an extended blackout. You can have a look at all of these options that are available by simply going to this web address. Ready to go beyond just solving problems? If you've been following my daily posts and enjoying the sample problems, you're going to love this. All of these problem sets and more are now available on my official course site, my stand store for electrical training. You can go to this website by tuning into the web address that you see at the bottom of this slide, https://stand.store/GVB.